So to give some specificity to these general models for caches, let's look at several architectures that are common in practice that have specific designations. The first of these is a direct map cache. And a direct map cache's defining characteristic is that the value for E, the number of lines per set, is just 1. So as you can see here in this illustration, I've got S sets still, but each of those sets has only one line in it. So the number of lines per set, exactly 1. That's going to simplify the process of looking things up in this cache, because we can essentially skip the step where we have to match a bunch of different lines simultaneously. So what we would be doing if we were given this address is initially, as I've said before, take a look at the set index and use that to select a particular set within the cache. Once we have figured out which set that is, we can then compare the tag bits in the address with the tag in that line. And now, again, because we've got E equal to 1, there's only one line to match against that tag. If the tag matches successfully, then we're going to also look at the valid bit. If that valid bit is not set, it's a cache miss, and we're going to look in the next layer of the memory hierarchy lower. If the valid bit is set, if it's a 1, then we've found the location of this address in this cache. Now the next thing to do then is to fetch out the value from the block within this line of the cache. And the block offset is where we're going to go to figure out which of the bytes in the block correspond to the address that's being requested. And because this is set to 100 or 4, we're going to skip to the 4th byte. And how many bytes are we going to read out? Well, that's going to be determined by the request being made from the layer above. And I'm assuming here, as I've indicated, that we're looking at the address of an int. So somewhere in the assembly language that's requesting this memory location, we've asked for a 4-byte value to be retrieved from memory. So we have the offset of the first byte of that value, and the size of the instruction, the L in the move L instruction, for example, is going to say move a long word, which is going to get 4 bytes, and it'll get those 4 bytes from that first location as indicated by the block offset. And that's what's going to be returned to the layer of the memory hierarchy above us. Now, it's also possible that there's a cache miss. In other words, that either we didn't match the tag, the valid bit wasn't set, and in that case, we would have gotten rid of this line from the cache at this level and fetched the value from the cache layer immediately below us in the memory hierarchy, which might have in turn gone and fetched values from other lower level caches. But what's going to happen eventually is that request is going to be satisfied, and we're going to replace this block with the value that comes up from below in the cache hierarchy or the memory hierarchy, so that in the future we can satisfy requests for this address range from this layer of the cache. Okay, let's look at a simulation of a really simple example of a direct mapped cache. I've got an M of 16, which means I just have 16 bytes in my memory, so super powerful 16-byte computer. The cool thing, though, is that with only 16 bytes in memory, I can get away with a really small address, which is going to make it easy to simulate. So 4-bit addresses allow me to access one of 16 bytes in memory. Direct map cache, so I've got one line per set, and then I've got 4 sets set up here, set 0 through set 3. So because I have 4 sets, I know that means that my value for little s is going to have to be 2, because 2 to the 2, or 4, is going to be my total number of sets. The fact that this is 2 means that I have to have 2 bits in my address. Here in the encoding that I'm showing from before, 2 bits of the address are going to be an index to pick out the set in the cache, such that if the value stored at a particular address is in the cache, it's going to appear in that set. Of course, because this is a direct map cache, that's going to restrict our search to just one of the 4 lines in the cache. You also see that I've got a block here that's just got 2 bytes in it. So my bytes per block up here, 2 means that I have to have 1 bit in my address that's going to pick one of those 2 bytes to determine which of the values in the cache is being addressed by the next layer up in the memory hierarchy. And then because I now have 3 bits occupied of my 4-bit address, I have 1 bit left over for the tag bit, which is going to get stored here in the cache lines. So what we're going to do is just walk through an example of a particular pattern of memory addresses. So to start out, I'm going to assume that the layer of the memory hierarchy above me has asked for the value at address 0. So the bit pattern, of course, is just all zeros. So let's follow the algorithm that we've been talking about that indicates how we go and look in the cache. Well, the first thing we're going to do is find the set, and the 2 inner bits of the address, these 2 guys, are just zeros. So that's going to pick out set 0. Now in set 0, I'm going to go and see, well, is the tag bit, does it match the tag that's there? Well, this tag bit hasn't even been set yet, really, and I can also see that the valid bit is 0. So right away I know that the cache is not storing the value for this particular address. The only place that it could appear, if it is in the cache, would be in this set, because that's what these 2 bits are indexing. And the fact that the valid bit is clear means that there is not a valid copy of those 2 bytes of memory, or those 2 bytes from the lower level of the cache in this level of the cache. So it's going to be a cache miss. Now, in addition to that, after determining that the cache missed, the caching hardware is going to request of the lower level, the level below this in the memory hierarchy, the actual value for address 0000. So it's going to make a request to that lower level cache. It's going to receive the value back from that lower level. And because we're using a bytes per block number of 2, we're not only going to get memory address 0, which is what we're really requesting, we're also going to get memory address 1 and store both of those in the block that's selected by the appropriate set. We're also going to set the tag bit to match the topmost bit in the address. So that's set to 0, and we're going to mark this entry in the cache as valid. So it's got a 1 in the V bit. Okay, now time for another address reference. We're going to ask for address 1. Again, walk through the pattern. The innermost 2 bits in this case specify the set index. So we're going to go back to set 0. We're going to check to see if, since this is the only line in that set, we're going to check to see if the tag bit matches the tag bit that's there. It's a 0 in the address. It happens to be a 0 there. And the V or valid bit is also set. So that corresponds to a cache hit. The previous address at access at location 0 brought in this block of 2 bytes, and that meant that when we went and asked for address 1, that was already here in the cache from the previous memory access. Now let's access address 7. Well, same process. The 2 innermost bits here that are our set index in this case indicate that we want to be looking at set 3 here, and we know, again, as was the case for the first memory access, the fact that this has a valid bit of 0 and that this is the only line in the set means that there's a cache miss that's happening here. So the cache is going to miss, and we're going to ask the next level lower in the memory hierarchy for the value at that address. So we pass it to the lower level. It's going to give us back whatever it found at address 7. And it's going to store that here in the block in set 3. Oh, there was the miss. Here's the values that were brought up. So it's going to grab address 7 and the corresponding byte at the adjacent memory location. It's going to set the tag to be 0, because the tag bit in this address is 0. And it's going to set the valid bit to be true. Okay, now let's get address 8. Well, same pattern. Look at the zeros in the middle. That's going to give us this set. Next, we're going to check to see, well, does the tag bit of the only line in that set match the tag bit in the address? Well, the address has a 1. The tag bit here is a 0. So since that's the only place that values from address 8 could be in the cache, we get a cache miss. We're then going to go and read the value at address 8 from below, and that's going to come up from the layer below in the memory hierarchy, and we're going to store the values at address 8 and 9 in the cache. We're going to set the tag to match the tag bit of the memory we just read, and we're going to maintain the valid bit as set. Notice that both address 0 and address 8 resolve to this same line of this set 0 in the cache. That's just a necessary side effect of the way caches work. There's going to be conflicts where multiple locations in memory are going to map to the same locations in the cache at certain times. Another address, now we're going to go back to address 0. And although we're seeing some temporal locality here, right, we've gone back and accessed address 0 again fairly quickly after we accessed the first time, we're running into a cache conflict here because we just got rid of the value in the cache that was stored at address 0 so we could fit the value from address 8. So we're going to go through this process again, 0, 0 for the set index. It's going to pick out this set. The tag is not going to match even though the valid bit is set. We're going to call this a cache miss, and then go and ask the next level down in the hierarchy for the value of that particular address and bring it up into this same set. So the valid bit maintains a 1. We've now got the values from memory address 0 and memory address 1, and the tag bit corresponds to the higher order bit of the address. The next example of a common cache architecture is called the set associative cache. And the distinguishing characteristic of this type of cache is that the value for E, that is the number of lines per set, is going to be greater than 1. So in this simple example, again, we have a value for S that gives us the number of sets in the cache. And in this case, I'm showing E equal to 2. So we've got 2 lines in each set. Okay, we're going to use the same basic pattern for accessing this cache. It's a little bit more elaborate than the previous one because we've got multiple lines per set, but the principles remain the same. So the first thing we have when we receive an address at this level of the cache is to use the set index bits to pick out the particular set that we're interested in. And again, if the address that's being requested from above is anywhere in this cache, it's going to be in that particular set that is indicated by the set index bits. Next thing to do after we've picked out that particular set is to check to see if the tag in the upper portion of the address matches any of the tags in the particular set. So the hardware is going to simultaneously check to see if these bits from the address match the tag bits in this line of the set or this line of the set. And that's a characteristic of these set associative caches. We're going to do a parallel comparison of these bits in the address with the tags on the selected set simultaneously. Let's say that the tag matches this line. Make sure that this is a valid line by just looking at the valid bit. So if that's true, if it's set to 1, we've found a matching line in the cache. We're then going to grab the block offset from the least significant bits of the address and use that as an index into the block to pick out the particular bytes that we want to return to the layer above us. If, for example, we were asked to fetch a short, a 2-byte value, we would get the value at location here 100 or 4, so offset 4, and get the 2 bytes starting at that offset and send it back up to the layer above us. Notice that if the cache misses, as before, we're going to select some line from the cache and throw it away and bring up the appropriate entries from the lower level in the hierarchy and replace that line in the cache at this level. Let's look at a simple simulation of a set associative cache. So in this case, I've got a cache architecture that has 2 sets, each of which has 2 lines. And I'm using the same setup as before, where I've just got 16 bytes of memory and a 4-bit address. Because I've got 2 sets, we can see up here in the legend that I want to have a single bit that's going to choose between the sets. I either want to get set 0 or set 1. So that means in the partitioning that I'm going to employ for the address, I just have 1 bit now. The 1 to 3rd bit in the address is going to choose the set. And I still have 2 bytes per block. So my block offset is also going to have 1 bit to pick either this byte or this byte. And that leaves 2 bytes left over for the tag bits. All right, so same pattern. We're going to start out by looking at address 0, all zeros in the address bits. First step is to figure out which set that address could be in if we have it in the cache. So I'm going to look at the third bit here, which is a 0. That's going to tell me I'm going to use set 0. So the next step then would be to look to see if any of the lines in that set have a matching tag. But I can see right away that I can ignore both of these lines because they both have a valid bit of 0. They haven't been used yet, haven't been initialized yet, so we can immediately conclude that we've got a cache miss. As a result of that miss, we're going to go and fetch from the next lower level in the hierarchy the values that are at address 0. So we're going to go down to that next layer, and we're going to store in a line of the set the two values from memory that include address 0. We're going to set the valid bit to true, and we're going to set the tag to match the tag bits from the address. And in this case now, these top two bits are the tag bits, and that's what we store here in this line. Now notice that we could just as easily have brought that cached information into this line instead of this line. It doesn't matter at all, and we'll talk later about how we might wisely choose which of these to use as the appropriate line within the set. Again, it's important to keep in mind that once we have determined the set that address could be stored in based on the set index, that we only have available to us choices of the lines within this set. That particular address, because this third bit is a 0, is only ever going to get stored in this set if it's in the cache at all. It's never going to appear in this set. Next address 1. Same process. We're going to look at the set bit. It's still a 0. We want to then compare the tag bits. We can compare those with the tags in the set. We've got a match here. That particular line has a valid bit set. So we know that this is legitimate, and we can fish out this byte from the block to return to our caller. So that's a cache hit. Then the next address we've accessed is address 7, and we can see from this that the set index bit right here is a 1. So if that address has been cached in this cache, it's going to be in this set. We can see right away that it's not here because none of the lines in that set are valid, so we'll kind of skip to the fact that that's going to be a miss. So we're going to then fetch up that part of memory from the layer below. And again, we can arbitrarily choose either of the lines within set 1 to store that information. So we're going to bring up the values for memory addresses 6 and 7 that correspond to this request. We're going to set the tag to match the top two bits in the address because that's our tag field, and we're going to set the valid bit to equal 1. Now we're going to address address 8. You remember from before that address 8 and address 0 collided in the 0th set. In this case, however, we've got two lines in that set. So let's look at the set index bit, which tells us it's going to go in set 0 as before. And we're going to look in here and see, well, we've got a tag of 0, which does not match the tag bits from this address, and the other entry is invalid, so we're going to conclude that this is a miss. We're going to then go fetch address 8 from below, and what we're going to do is choose to use the unused line of set 0 to store that value. So we get addresses 8 and 9, and we're going to set the tag bit to correspond to the tag bits of the address and mark the set as valid. Now we're going to access address 0 again. So this is where we had a miss before because the reference to address 8 had evicted the entry for address 0 from the cache. But now that we have two lines in each set, we see that we've maintained or retained the value that was cached for address 0, and it wasn't clobbered by address 8 because we have a separate line for it. So obviously we're going to look at the set index bit, find that it is going to be this set, look at the tag bits, it's going to match this line, the valid bit is set, and we get a cache hit. The final example is that of a fully associative cache. So this is kind of the opposite extreme from the direct mapped cache in a way, in that it has all of the lines in just one set. So you can see here that the number of sets, big S, is just 1. So on the left-hand side here, you can see s equals 1. There's just one set, and within that set, we have a whole bunch of lines. In fact, the number of lines is just going to be the cache size, C, divided by the number of bytes per block. Okay. Now our address interpretation gets a little bit different here. Because we have just one set, you'll notice that the calculation that we normally apply here to say that the number of sets s is equal to 2 to the number of bits, the exponent little s. Now that we have only one set, the exponent we're going to use is actually 0. So there are no bits that are going to select the set, which makes sense because there's only one set to select. There's no point in interpreting anything from the address as a particular set because we only have one place to look. So the address interpretation then gets a little bit simpler. We don't have any set index bits. We still have our block offset, but all the rest of the bits are going to end up being tag bits. So we're going to simultaneously search all of the tags for matching bits from the address, and if we find a matching tag where there's also a valid bit that's set to true, that tells us we have a cache hit. So you can see that this is kind of the opposite extreme from the direct mapped cache, where we have only one line per set. Here we have all of the lines in the same set. So here would be an example of how we would reference this. Whenever we get an address in, we're going to immediately skip to the point where we match the tags, right? We don't have to figure out which set it lives in because there's only one. So again, as before, we're going to simultaneously compare the tag bits in the address with all of the tags in this set. That's no different than what we did in the set associative cache. It just seems a little bit more elaborate here because presumably we're going to try to match simultaneously a whole bunch of tags in the cache. If we find a matching tag that has a valid bit, then we're going to go to the block offset, which I'm showing here as 100 again, so offset number 4. And again, let's imagine we're being asked to fetch a short integer or 2 bytes. So we're going to grab those 2 bytes from the line of the cache that had the tag that matched the tag bits and that had a valid bit set, and return that up to the layer of the memory hierarchy above us. And as before, if we have a cache miss, we're going to pick some line from the cache, throw it out, and replace it with the response from the layer immediately below us in the memory hierarchy. So let's look at a real-world example of a cache architecture. And for this discussion, we're going to look at the Intel Core i7, which is a generation or so behind the times right now, but it's still an interesting memory hierarchy. We can see that we've got multiple layers in the hierarchy here. So this pyramid, just like before, shows smaller, faster, more expensive things higher up and larger, slower, cheaper things lower down. And we can see that we've, of course, got a register file in each core. Then there's going to be 3 levels of cache, L1, L2, and L3. And all 4 of those things are stored on the chip, and they're implemented as SRAM. Once we get off the chip and go out to main memory, then, of course, we're going to use DRAM, which is going to be larger and cheaper. So to start with, let's look at an individual core. The i7 can have multiple cores, but we'll just think about one to start with. So of course we have the register file. Got to have registers for the ALU to talk to. And the register file is going to refer to memory by way of a level 1 or an L1 cache. And what we see in this architecture is that we have 2 L1 caches, one for data and one for instructions. And the reason for this is that it's going to often be the case that the location in memory of the data that we're accessing is not going to be anywhere near where the instructions are going to live in memory. So if we merge these together into a single cache, there'd be potentially a lot of cache misses due to conflicts between the locations of the data and the locations of the instructions. So we separate these apart to try to improve our hit rate and avoid having collisions in the cache. Each of the cores also has a layer 2 or an L2 cache, but it's a unified cache. In other words, it stores both data and instructions. And this same architecture is stamped out in each of the cores that are on the processor. So if we have a 4-core i7, each gets its own L1 data and L1 instruction cache here, here, and here, and each has its own L2 unified cache. Now if the L2 unified cache has a cache miss, it's going to in turn go and request information from a layer 3 cache, the L3 unified cache. And this guy is shared across all of the processor cores. Here are the characteristics of the Core i7's cache hierarchy. So at level 1, we've got 32K of memory. It's an 8-way set associative cache. In other words, each of the sets has 8 lines in it, and the block within each line is 64 bytes. So when we fetch something up from layer 2 to layer 1, we're getting 64 bytes at a time, which again is the source of our ability to satisfy temporally local accesses to memory. And the approximate time to access a value from layer 1 cache is 4 ticks of the clock. When we go down to the layer 2 unified cache, we see that it's quite a lot larger. It's 256K. It's similarly an 8-way set associative cache where the block size is 64 bytes. And to get a value out of this layer of the cache, it takes about 10 ticks. So if a value is already in the register file, it's basically available for free. If it's not in the register file, but it's found in the L1 cache, it takes 4 ticks. If we have to go down to the layer 2 cache, it's going to be about 10 ticks to respond with the appropriate value. And then at layer 3, this is quite a lot larger. It's 8 megabytes, and it's a 16-way set associative cache, which again has a 64-byte block size and takes between 40 and 75 ticks to respond to a memory request. Now, if the layer 3 cache doesn't have a value that's being requested by one of the cores above, it's going to then fall back to main memory and make the longer lasting memory request, which could be 2 orders of magnitude slower than what's going to be available in the register files. Here's a micrograph of the Core i7. It's a little hard to tell exactly what's going on here, but these are actually the physical circuitry that's put down on the surface of the chip. And we can kind of overlay this with a map of the basic pieces and parts. So here we've got the 4 cores are located as seen here. These include both an ALU, a register file, and an L1 and an L2 cache. My suspicion is that this area is probably the ALU and register files, and in the areas where you see sort of replicated units, that's probably a cache memory. Circuitry up here is the memory controller. So this was the interface to the rest of the memory system. So when we want to fetch something out of main memory or talk to the I/O bus, it's going to go through the circuitry up here. And then down at the bottom is the L3 cache. You can see that this is quite a lot larger than any of the caches that might be inside these cores. So far we've been focused on reading from the cache, but there's also some interesting problems that come up when we think about how do we write out to the cache. The principal challenge here is that we might have multiple copies of data in various parts of the memory system. We might have stuff in L1 that's also in L2, that's also in L3, that's also in main memory, that might actually also be out on disk still. And the game here is to figure out how do we ensure that there's consistent information being read by the processor regardless of what's going on at various levels of the memory hierarchy. We can think of this in sort of 4 cases, right? We're trying to do a memory write. When we're writing into a cache, there's a couple possibilities. The cache is either already got that location of memory, which we would say would result in a cache hit, or that location in the cache does not yet have that location in memory that we're trying to write to, or it's a cache miss. And we'll see that there's a couple of different strategies for dealing with both hits and misses that are usually paired together in particular ways. So let's think about the case where we have a cache hit. So this case down here, we try to write something to the cache, and we find that that address that we're trying to write to is already in the cache. There's 2 common possibilities. One's called write through. The idea here is that we're going to write immediately to memory. So we're going to go all the way from the layer of the memory hierarchy that we're trying to write into, and we're going to send that value all the way down to the RAM on the motherboard. We're also going to update the cache so that if we have to write again to that location, we'll already see that we have a write hit. The other possibility here is what's called write back. So we're going to only write to memory when we are about to throw something out of the cache. Only when a line in the cache is about to be evicted because we have to use it for some other portion of memory. This is an architecture that's a little bit more complicated because we need what's called a dirty bit, and that's, if you're a Monty Python fan, that's a joke, kind of, but that's actually the term of art that we use to refer to this. The line of the cache, in addition to having a valid bit, is going to have another bit that says, have the values in this line been changed since last we read from the level below us? You can see that there's performance implications for these two variants on what we do with a cache hit. If we write through, we're going to pay the price of a memory access with every write. That's going to maintain consistency sort of for free, but it's going to potentially take longer, so the performance is poorer. If we do write back, we've got to deal with some additional complexity because we have to keep track of whether or not the information in the cache is different from the layers of the memory hierarchy below it. But we only are going to write out to the memory system, to the main memory, when we're going to get rid of the current contents of a cache line. So if we're writing repeatedly through temporal locality to the same location in the cache, this is a big win because we're only going to write to memory when the cache line gets evicted. The other designs here deals with the case where we have a miss in the cache. In other words, we're going to try to write into the cache and the address that we're writing to is not yet in the cache. So again, we have two possibilities here. One is called write allocate. What this is going to do is go out to memory, load the line that's of interest into the cache, right? So it's going to deal with the fact that we have a cache miss, and then it's going to update it. On the other hand, we could say write no allocate, which basically says, okay, I didn't find this in the cache, boo-hoo, let's just go straight out to memory. And it's never going to load the line into memory at all. Now again, there's performance implications in these two cases. The write allocate is going to be good if we're going to be writing a bunch to that same location in memory, because if we bring it in to memory once, we can update it in the cache. Whereas write no allocate is going to be simpler, but probably more expensive because we're going to always pay the price of a write, and we're never going to load the line that we're writing to into the cache from main memory. It turns out that these four designs for memory writes in the cache are often used in pairs. So we'll often see write through and no write allocate used together, because we're, in both cases, writing immediately to memory. And we'll often see write back and write allocate being used together because in both cases we're sort of deferring the write until we absolutely have to push stuff back out into memory from the cache. Finally, let's talk about some performance metrics for caching. So the first one, and most common one that you'll hear referred to, is called the hit rate, and this is basically just the fraction of all memory references that are found in the cache. And you can calculate this by the number of hits divided by the number of accesses. Straightforward. There's also a corresponding miss rate, which is the fraction of references that are not found in the cache, and this is defined as the number of misses over the number of accesses, which you can see is also 1 minus the hit rate. The typical values for these things can be really quite small, so the miss rate in L1 cache can be as low as somewhere between 3 and 10%. Not super great, but by the time you get out to L2 cache, the miss rate can be quite small, like under 1%, which means that 99% of your cache accesses are going to be hits. Some other metrics have to do with the time instead of the percentage of hits. So the hit time is basically the time to deliver a value from the cache to the CPU. So the elapsed time from the time the CPU makes a request to the time that the value returns from the cache subsystem. And this includes the time to search for the appropriate information in the cache. And typical values, again, for an i7 are about 4 clock cycles to get from L1 cache, 10 clock cycles to get from L2. If we don't get a hit, we pay a miss penalty. So this is the additional time that's spent as a consequence of a miss in the cache. If we have to go all the way out to main memory, there's typically going to be a delay of between 50 and 200 ticks of the clock in order to get information out of main memory. So we'd really like to have a lot of hits. So what that says is there's a huge difference between hits and misses, like a penalty of almost 50 times between going to L1 and having to go all the way out to memory. The asymmetry between the hit time and the miss penalty gives rise to some interesting statistics that you kind of wouldn't expect. It turns out that if we have a 99% hit rate, it's actually twice as good in terms of performance as a 97% hit rate. So for example, if we have a hit time of 1 cycle, which is better than what we get in the i7, but let's just assume that for argument, and a miss penalty of 100 cycles, then let's think about the average time to make accesses to memory based on these two values for the caching hit rate. If we got a hit rate of 97%, then on average, we're going to get our value from memory after 1 cycle, but 0.03 of the time, we're going to have to pay the 100 cycle rate. So 1 cycle times 0.03 times 100 gives us 4 cycles on average if we're getting a hit rate of 97%. In contrast, if we get a hit rate of 99%, we're still going to pay the 1 cycle for all the hits, plus, over time, an average of 0.01 cycles because of the 1% miss rate times the 100 cycle penalty, resulting in an average access time of 2 cycles. So just getting from 97 to 99% doubles the efficiency with which we're going to access memory. So here's just some hints about writing cache-friendly code. We want to make the common case fast, right? So thinking back to the example of the summing of a two-dimensional array, we focused on the inner loops and made sure that the inner looping was taking place in such a way that the accesses to memory fit nicely in the way that the values were stored in memory, which is therefore going to improve our locality and get better hit rates out of the cache. We also want to minimize misses on those inner loops. So repeated references to variables using temporal locality. This was the example that we saw where the index control variable of those loops was being used repeatedly. And then we also saw that we're using what are called stride 1 reference patterns. This is basically just the notion that we're going to go from one location in memory to the next, to the next, to the next. That's stride 1, instead of making very large jumps from one location of memory to another far away, which is going to preserve spatial locality. In summary then, our qualitative notion of locality, right, we have a very kind of general idea of this now, of spatial and temporal locality, gets quantified when we think about how that locality maps down to our understanding of what takes place in the cache. So again, this is an indication of the utility of being able to think about what's happening under the hood as we're writing our code at the source level. If we really get what's happening in cache, we can write our source code in a way that ensures that we're getting good locality when the code actually runs on the hardware.